Good afternoon, gentlemen. My name is Partik, this is Pooja, and this is Madhvi. And we are TAPS, a zinc oxide-based piezoelectric nanogenerator for touchscreen devices. So let me ask you a question today. How many times in a day are you charging your electrical devices? We find that more and more of today's generation tend to recharge their electrical devices more often. So today we'll talk to you about why that is, the problem behind it, and what the market size is like, and the analysis. Then we'll get into the existing solutions that are out there in the market and how they tend to solve this problem. Then we'll get into what the customer requirements are and what the customers actually want. Follow that with our solution and how we address those requirements. And we'll then get into an analysis of the engineering and our methods that we use to design those. And then we'll conclude with a verification of those designs, followed by an analysis of the results and our future and next steps for TAPS as a company. So, like I said, how many times a day are you recharging your mobile device? We find that the average usage is approximately 4.7 hours, and that's an average. So the new generation nowadays is using much more than that. They're using approximately 10 to 12 hours on their device, on Facebook, social media, YouTube, and they're constantly texting away and constantly using their phone. However, the problem is that current lifetime of a battery in a cell phone or a mobile device is not that large. It's approximately 6.5 hours on average. Some have larger and some have less. And again, like I said, data shows that 81% of users are recharging their device a lot often. And the main thing is you cannot always find electrical outlets when you're out and about in the real world. So how do we tackle this? Well, currently there are existing solutions. So you can have a solar panel pack, a battery bank, wireless charging, and fast charging. But there's problems to all of these. With solar panel, yeah, you have the mobility, you can carry it around everywhere, but you're not getting the efficiency. It's not truly wireless because you have to still plug it into your phone. And the charge capacity isn't there as well. You need a long period of time to charge it up and then throw the energy into your phone. Now, power banks, those are amazing. You can get approximately 10,000 milliamps, 20,000 milliamps in one little package. And yeah, it supplies the power, but it's not wireless because, again, like I said, you have to connect it to your phone, right? Now, wireless charging, yeah, great and new technology, but you need a base, right? You need to have that base connected to either a computer or a wall outlet, and you need to place your phone on that base. That range isn't there yet either. So cell phone companies thought, how do we tackle this? They said, okay, let's try fast charging. Now, this is where you plug in your phone into the wall outlet, and within half an hour, you get a 60% charge, right? But still, you need a wall outlet. And that's not what we're going for here. So we went out and asked. We asked people, what are they looking for in a device that they would want to carry around with them? And they said that they want a device that's lightweight, mobile, easy to integrate within their current device. So they don't want anything extra. They want to use their device, and that's it. They want to have sufficient power output that they can sustain their phone throughout the day. Easy and safe to use, and most important, transparent. They're tired of looking around and seeing that huge power brick that they have to carry or an external power case that they need. So we said, okay, we'll help you. We'll tackle that issue for you.
Okay. So based on these customer requirements, we thought about ways in which we could develop a solution that would allow for an easily integratable solution into the screen so as to eliminate the need to carry around these chargers and additional devices. So this film would need to be thin and still generate a sufficient amount of power while having transparent components. The electrodes need to be transparent, and so does the energy generation mechanism. So hence, we've decided to use transparent ITO electrodes with piezoelectric zinc oxide nanowires sandwiched between them. The zinc oxide nanowires are known to be highly transparent with good piezoelectric properties for mechanical energy harvesting. In order to make this device safe for consumers to use, the nanowires would need to be isolated from the environment, and this is done by adding a PDMS outer layer. And this solution would meet many of the customer requirements that were set and enable continuous charging while the device is in use. And the fabrication cost of one standard smartphone screen size film would be about $8. And this can be further decreased by purchasing materials in bulk or expanding the production process. So you might be wondering as to what piezoelectricity is and how it actually works. Piezoelectricity, also called the piezoelectric effect, is the appearance of an electric potential across the sides of a highly crystalline material when it is subjected to mechanical stresses by compression. In practice, the crystal becomes a kind of tiny battery with a positive charge on one face and a negative charge on the other opposite face, and current flows if you connect the two faces together to make a circuit. This technology has potential applications in high voltage and high power devices and sensors, actuators, and piezoelectric motors. Piezoelectric nanogenerators commonly use PVDF, gallium nitride, and zinc oxide as their materials. Zinc oxide nanowires have the advantages of being semiconducting and having a high piezoelectricity. And nanowires with a high aspect ratio can be grown while still maintaining a high level of crystallinity. And zinc oxide nanowires are also considered to be biocompatible. There are several methods for growing zinc oxide nanowires. And high aspect ratio nanowires with a high degree of crystallinity can be grown in arrays by potentiostatic electrode deposition on an anodic aluminum oxide template using DMSO solutions with precursors that are in there. They can also be grown by using electrospinning and hydrothermal growth. And hydrothermal growth of zinc oxide nanowires has the advantage of having a low cost and a very simple procedure to follow, where it uses a low temperature and pressure. And adjusting the growth time allows for control over the length of the grown nanowires, and as a result, the hydrothermal growth process is the process that we've used in our fabrication process. So hydrothermal growth of the zinc oxide nanowires starts with seeding an ITO-coated PET substrate, and the more number of seed layers that are applied, the better the surface coverage and nanowire distribution on the electrode. So it is suggested that the ITO-coated PET substrate be subjected to seeding process at least 5 times, and then the hydrothermal growth process be carried out. So for hydrothermal growth, the oven temperature is set to 90 degrees Celsius, and the seeded ITO-coated PET substrate is suspended in the nutrient solution, which is made from 15 millimolar zinc nitrate and 15 millimolar HMTA in DI water. The wires are grown for at least 6 hours to ensure a minimum length of 1 micrometer for the zinc oxide nanowires. After the growth is complete, the film is cooled to room temperature, removed from the growth solution, and cleaned to remove any precipitate that's on it. The growth is then characterized by SEM imaging, and the film is then used for completing the assembly of the prototype. Here's the engineering design analysis that was conducted when trying to meet the customer requirements. The assembled product had to be able to convert from mechanical inputs to electrical energy, and with piezoelectricity, it's generally the case that the larger the mechanical stress applied, the larger the current generated will be. However, this needs to be balanced with the durability of the assembled prototype, as the larger the compressive forces applied, the more likely the device gets to being damaged. Next, it was decided that the product must have at least 60% transmittance, so the trade-off between the visibility of the screen display and the image resolution is not compromised, and it's at an acceptable level. The film will be made to be of a thickness of 0.5 millimeters or less, which is typical of a standard screen protectors, so as to ensure that the touch sensitivity of the device is not hindered. The film is to weigh no more than 10 grams, which is the typical weight for a standard screen protector again. And this is to ensure the portability of the product is not affected significantly. And the nanowires will also be sufficiently isolated so as to ensure the safety of the user. and the 0.05 millimeter thick PDMS layer applied on the outside will achieve this.
So how did we go about verifying this analysis? First, we looked at characterizing zinc oxide nanowires with an SEM. Then we moved on to the electrical output charges. So we looked at the current, voltage, and also we recharged the capacitor using our device. We next moved on to physical properties of the film. So we looked at the thickness, weight, and lastly, we looked at UV, so that optical transparency that the customers require the most. So when looking at the SEM images, you'll see here there's two different sets. They're both after growth. One is before cleaning and the other one is after cleaning. So the one that's before cleaning you'll see is very cloudy, and I don't know if the lighting is okay, but the before cleaning cloudy is due to the fact that there's still seed solution still on the wires. Now, the wires still generate current and voltage, but we notice that once we create a method of cleaning off the seed solution, there's a higher contrast leading to a higher bending of the wires and higher output. Secondly, we also noticed that with this growth method, we achieved approximately 200 nanometers in diameter and 1 to 4 micrometers in length. So for us, that was a high aspect ratio, and we do hope on improving this with further iterations of our prototype. Lastly, we see with the middle after being grown image that it is somewhat of a dense and populated nanowire growth. However, with further iterations, it will become even more densely distributed with longer nanowires, approximately 7 to 10 micrometers and 500 nanometers wide in diameter. We also looked at voltage and current output. So the voltage output that we first attained was 25 millivolts to approximately 400 millivolts. Now that number has changed. So if you have time and go look at our prototype out on the stands, you'll see that right now we're achieving 1 to 6 volts with each tap. And that is just because of our current process. We improved it. And the final prototype that we have, the wires are much more densely packed and longer. So we are receiving higher voltage output. However, our current output is still not adequate. We're still receiving approximately in the microamp range. And we do hope on improving that in terms of, again, having longer and larger nanowires with a higher aspect ratio and having them aligned, more densely packed, and allowing for them to be vertical. Because right now, they're not truly vertical. So if we can achieve that vertical growth, that is ideal. Next, we did look at charging a capacitor. This proved a little problematic because this was one of our primary prototypes, and we did receive some charge, but it was quite low, 25 millivolts. And since the device itself is AC current, we had to use a rectifier diode bridge to convert it. And we did lose some of the current and voltage, but we managed to get a 25 millivolts charge and discharge rate of the capacitor.
With regards to the UV-vis measurements, they were taken primarily to quantitatively assess the optical transparency of the device. And the initial prototype that was not cleaned after the hydrothermal growth process displayed a 59% transmittance at a wavelength of 550 nanometers. The final prototype that was subjected to further cleaning to remove the precipitate after growth displayed a 79% transmittance at the same wavelength. This exceeds the minimum limit of 60% transmittance that the customer desires. And note that the wavelength of 550 nanometers was used, as it is the industry standard wavelength at which transmittance is generally reported. The device thickness was measured at different positions on the film using a vernier caliper, and the average thickness was determined to be about 0.36 millimeters, and this is better than the expected range of 0.4 to 0.5 millimeters.
So where do we stand right now? Out of our primary, tertiary, and secondary requirements, we have achieved 80% of what we stated we would. The only things that we were not able to achieve were the battery recharge capacity. We were aiming at 300 milliamp hours, And the output, we were hoping for 5 volts and 550 milliamps. The 5 volts we have achieved if you come outside and look at our demo. However, we are still working on achieving the 150 milliamps and the recharge capacity. So with a more efficient fabrication process and better nanowire distribution, we hope to achieve this. So in terms of steps for the future, we're looking at increasing the number of film layers or seeding layers. So rather than 5, add on another 5. So we have a larger distribution of seeds that the nanowires will grow from. Increase the growth time. So right now our growth time in the hydrothermal solution is approximately 8 to 9 hours. So we're hoping to increase that to 12 to 16 to get those longer nanowires that we need. And potentially incorporate this into all and any electronic device. So your phones, your tablets, your computer screens, your wearable electronics. And lastly, incorporate this into potentially all non-transparent surfaces. So for example, the keyboards on a laptop or the walking surfaces of your home. As you walk, you generate electricity to power some of the electronics within your house. So to conclude, just remember, there are many problems in the world today, but a dead phone shouldn't be one of them. Thank you for listening. We are TAPS, and all questions are welcomed.
Thank you very much. Questions? Do you patent your nanowires to make the device?
We haven't.
So like, you grow these nanowires on the substrates, right? Then you use the whole substrate to make one device, or
Whole substrate.
patent it to make a few devices.
No, whole substrate.
No,
So,
we use the whole
yeah,
entire
we use the whole
substrate.
substrate. So we have let's say, a 3x4. Sorry. Well, we use a 3x4 piece of ITO, and we apply our seed solution, and we flip it over into a bath of our solution. And at 100 degrees, we let gravity do the work, and it just grows.
There's no shortage problems associated with such a big area?
Yeah, and we do notice that there are some patches where the nanowires don't grow. So that's why we hope with, like, in terms of applying a larger seed solution, that the seed covers everything. There's no 100% method to making it work in terms of that. If we apply multiple layers, it'll work. It just has to be an iterative process that we have to optimize. Yeah.
So you said that right now the output voltage is
1 to 6 volts, yeah.
Then how long does it take to charge this system?
So our initial calculations, the very preliminary, are approximately 1 to 5% of battery capacity over a 24-hour period. But like, if we're able to pick up our company off the floor and pursue this idea, we're hoping to, if we can optimize the fabrication process, get around 10 to 20% of battery capacity just from tapping it. So even tapping, and even also when you swipe your finger, it also generates. Yeah. So our hurdle is the current right now. It's very little. So if we can fix that, then we're golden.
What is the problem with this low current?
It's the wires. They're known to generate very low current. So I mean, if we can, from what I understand, if we can have a more dense array and distribution of nanowires, that potentially we can go over that hurdle.
Have you ever estimated this energy conversion efficiency? So you know what's the voltage, and you also know the current, but you don't know how much mechanical energy you apply when
Yeah.
and how much energy is transferred.
Yeah, that's something we haven't looked at. We should look at, yeah.
So in terms of actually harvesting this charge,
Yes.
which is effectively your current, over such a large area, if you have this piezoelectric layer there, don't you run into a problem of actually charge transfer over those surfaces?
Yeah, so one way we're thinking of avoiding that in our final product, well, first we ground, but one way we're actually hoping to avoid that is rather than making it apply on the surface itself, incorporate it inside the phone, so underneath the device itself. So you're not actually in contact, but you're in contact with the screen, and then underneath the screen you can apply.
Okay, so
Yeah.
basically it's got kind of like 2 electrodes on both sides.
Yeah.
Any more questions? Well, that was, pretty challenging. Very nice job. Thank you.
Yeah. Thank you.